welcome to the ongoing course of perception algorithms for autonomous systems. So, we completed estimation theory with multiple examples for radar tracking, for bearing angle only tracking in last few lectures. Now, this is a kind of a preparatory position thing to start the target tracking basics. So, once we start the target tracking basics, then it will be followed with sensor fusion and classification. So, with this our perception course will be completed. So, let me start with lecture 14. Welcome. So, what is the definition of a tracking? What do we know by tracking? So, tracking means, if you know the kind of tracking means, suppose I am kind of monitoring someone's position, someone's location, someone's velocity or everything. Okay. So, let us say the position only. So, I have some sensor measurements, those sensor measurements are noisy, and with the noise sensor measurements I would like to monitor or track the person's or the actual or the vehicles, what is the kind of trajectory or path he or she is following. So, this is the tracking. So, in a more formal definition, so you get some information about the motion of an object. So, when I say motion of an object, what are the motion, what can represent a motion of an object? Obviously, your position, your x, y, z position. If it is a ground object, then it will be x and y position. What else? It will be your velocity information, your velocity, your in all the three direction velocity information, if you want to go little bit more precise. Plus it will be your turn rate or yaw rate, or how, if the person is turning or this thing. So, what is the turn rate, yaw rate? And one very important thing is your heading. What is the heading or the orientation of the person or the vehicle, whatever you say. Okay. Acceleration is not a part of tracking, but at least position and velocity. Position is the main thing for the tracking, because you want to know the trajectory in a XYZ format. So, that is the main thing. However, velocity is also an important part, as well as your turn rate or your yaw rate or your heading. The yaw rate actually or the heading is derived actually from Vx Vy, from your velocity estimates, but it is also an important maneuver forcing function. So, when the target, because target can move in a straight line, it could go in a turn, it could again accelerate. So, the acceleration forcing function could be either your yaw rate, or if you want to do in a linear acceleration, then your Ax, Ay will come into picture. Okay. Now, there are two differences between a tracking and a navigation. Let me explain what is navigation, or what is called localization, what is called tracking. Localization is also position and velocity estimation, but with the host vehicle or the own ship. I will use the term own ship, it is very kind of popular term. So, that means wherever your sensor is mounted, suppose you are doing you are moving your car. So, how you will know the position of your exact vehicle, okay, with respect to say some global coordinate system or say AutoSAR some coordinate system and all. So, you will use some GPS say, or you will use IMUs, inertial measurement system, or you will use GPS data, or that will show in a map that this is your position. So, that is your tracking, but not the others tracking. And when I use the word, so this is called localization or navigation. So, localization or navigation is also the kinematic information, your position, velocity, turn rate, attitude, headings, everything, acceleration, everything. So, this is of your own ship, own vehicle. But when you want to kind of monitor for others, other vehicles or other objects, other targets, then it will come into tracking. So, in own ship you need your GPS or your or even your vision based systems or your inertial measurement unit to give your positions or velocities. Okay. But for tracking, when you want to do for others, then you need to have some kind of active sensors. So, these sensors could be your radar, it could be your cameras, it could be your UIR sensors, it could be your LIDAR, or even underwater scenario, or in a shipping scenario, it will be naval scenario, it will be sonar. So, the basis in the direction of arrival estimate, it will give you the target location or target information. So, with this, now what are the main challenges in tracking, that I will discuss in subsequent slides. One, an measurement is incorrect. So, your measurement is corrupted with wide Gaussian noise, and that means your measurement error, because this is your evidence what your sensor can pick up. with its electronics and with its hardware. Now, you have to mathematically go from your observation space or the evidential space to your hypothesis space. So, you want to estimate the truth. So, that is what your standard Bayes theorem or Bayes principle tells. So, probability of z given x is actually your likelihood, and probability of x given z is actually your maxima a posteriori. So, that is what you would like to estimate using Kalman filter. We already learned these things. Okay. Second problem is actually very important, which is called false alarm. False alarm is actually for, even it is possible for any kind of target. It is say in a aerospace scenario or even a ground tracking scenario, even for a naval scenario as well, naval scenario mostly, because you are measuring your position from your submarine or any kind of ship from some sound or from some kind of sound wave or even visual. So, there actually there is a chance of multiple false alarms, false echoes actually can come. Okay. So, maybe you can, if you remember some movie, some naval movies, one famous movie called Ghazi Attack. So, there you have seen that sonar operator always sitting in a headphone in a sonar room. So, what he is doing? He is actually trying to gauge the incoming submarine vehicle or from all other different water sounds. So, it could be from your fishing sound, it could be some torpedo sound, or it could be something else. So, how to move it, how to do it. So, this is a sonar tracking. Similarly, for there, so there are a lot of false alarms will come. I mean, false alarm is maximum in naval system. In radar also, it will be like this. For a fighter aircraft, if you go to a low altitude flying, you will be blind to the radar. The aircraft won't be visible to your radar. Beyond the because of the ground clutters. So, ground clutters are so much, you won't be able to see the tail tracker. You won't get any measurement. These are all sensor inaccuracies. Okay. But when you go little bit high, you will get it. Similarly, for airborne to air engagement scenarios. So, air to air engagement scenarios, what will happen? Suppose when suppose a missile, now a lot of wars are happening, you can see. So, when you are locking a target and you release your store or your missile or weapon. So, what will happen? That the enemy, the other aircraft, to which you have aimed, he will apply its decoys or shafts. So, they are nothing but a kind of false targets. Okay. These are all kind of a false targets. So, with that false target, that your missiles would think that okay, this is my target and he can escape. Okay. So, these are all kind of called false information or false alarms. So, with your target, it could be your target oriented measurements and some false measurements. Together, your sensor will give you a data. Now, you have to find it out. Your algorithm, now you have to write your algorithm, which one belongs to my current actual target, which is actually false alarm, or it could be so happen all measurements at a given scan will be of false alarm, they won't be any target. You have to find it out. So, that is the purpose of a target tracking. Okay. I will go into details in the subsequent sections. So, say this is a typical face tracking system using your say a simple camera, simple say monocular camera and all. So, your position of the edges are the kind of thing. So, you can see that edges are kind of marked and the person as the pedestrian or whatever say is moving. So, his motion is kind of getting tracked using the camera and the resultant tracking algorithm is telling what is your x position, x velocity, y position, y velocity, everything. This is a typical ADAS scenario. So, a crossing pedestrian is moving. So, this fellow is just crossing the road and you have a say this vehicle is having say some kind of either say camera, just a camera say. So, here actually you are kind of monitor, you are first detecting the object, you are creating the object, or it could be a radar also can be used. So, you are detecting the object and you are assuming, you are actually deriving what is this trajectory, this person is crossing. So, it is a crossing target. So, that it will identify and it is not inside my ego lane, nearby my ego lane, that means my driving path, ego lane means driving path. So, that I do not need to give my brake and all. So, this is the tracking. Okay. So, now target tracking. So, target tracking and prediction of an object, point, mass, motion is for using different sensor information we already covered. So, what are the parts of tracking? Obviously, filtering, your prediction, your estimation. So, your Kalman filter is an integral part or core part into the target tracking. So, this we have covered, we know Kalman filter now. We have solved examples, we know what is called prediction, what is called filtering. Next part what we will be telling today is, or in the subsequent classes, is that data association part. So, data association part means I just told using some practical examples, your submarine example, your radar examples and all blah blah blah. So, there you have seen that there could be measurements which could be from false target, there could be measurements which could be from true target, or there could be an instance where all measurements could be from false targets, or there could be thing that all measurements could be from true target also. But and this is for T1, if it is like this, T2 it will be changed, T3 it will be changed, because a sensor and different kind of a atmosphere, it can give you different measurements, okay, different clutters, different environment, your flying criterions and all, it can different measurements. So, now you have to choose your true target states. What is your true target position? Velocity. What is your true velocity from lot of false observations or false echoes, I will use the word echoes, false echoes, you have to find out true. So, this part is very important part, is called data association. We will learn it, how the data association is confirmed. Third and very important thing, I told it during the time of when I said the target maneuver models and target dynamics model basically. So, there something called, you need to now understand when the target has changed its course or it changes state. For example, target can be either go linearly in a linear motion, or it can suddenly accelerate. It can accelerate in a linear direction, or it can do a simply curvilinear acceleration also it can take. So, you can take a yaw rate and you can change the course. So, this is called maneuver onset. Now, I told that single model is not good enough, or single model based Kalman filter are not good enough. So, you need to have something different, either you have to go for an made for adaptive Kalman filter or some multiple model, that I will talk. So, solution is not important, that we will talk later. Okay. So, this is called, so you need to determine the change point or mode accurately. If you do not do that, then you will be losing the target from the behavior. So, this thing called target motion uncertainty. So, what is the data association? This is the sensor uncertainty, measurement origin uncertainty I will say, and this is called your target motion uncertainty. So, your tracking has to now cope up everything. Filtering estimation is Kalman filter is Next you have to tackle measurement origin uncertainty, and second you have to do the thing of the dynamic uncertainty. Okay. And after that, these are the sensors, that is all we have talked, we will not talk it further. Now, so tracking, as you know, you first have we will take the example a multi-target tracking. So, or it could be a single target tracking in presence of clutter, both are same. So, multi-target tracking is and the method used for multi-target tracking and single target tracking in clutter, single target tracking in both are same, the methods are same. Okay. It does not matter whether you have only one target or you have multiple valid target, does not matter, because you will have lot of false measurements and you have to find out which one is your actual target. So, it is just a game, some kind of statistical game, you need to find which is your actual target. So, this method is called data association, as I mentioned, and then target oriented measure. TOM is actually signifies the target oriented measurements, that you will find it out. So, which target, which measurement will be updated for which state, because our Kalman filter is confused. Kalman filter, you have prediction, you have measurement update or estimation. Estimation, you have to give only one measurement to your predicted state. Okay. And based on that, your innovation error variance will be calculated, your gains will be updated, your covariance will be updated, everything. Okay. So, which measurement you will give? You have now more option. You have say only one target, that also you do not know whether one or many, but you have a chain of measurements radar will give you. Now, which measurement you will use your Kalman filter to respond. Okay. So, that means which measurement you will use to marry your Kalman filter or marry your target. So, like this. So, you have to find the exact proper measurement set which will be used to update your actual target state. Okay. This is some presentation that I will show you what are the challenges in a multi-target tracking scenario. So, this is actually called clutter, that or the false alarm, what I am saying. So, this is your target space and this is your observation space. Okay. From the target space means actually it is actually hypothesis space or actual world which you do not know. You have a view of observation space, okay, in mathematical terms. Say you have at a given scan 5 targets are appeared within the sensor field of views. So, you see 1, 2, 3, 4, 5. So, this is at t equal to k minus 1, and when you go to t equal to k, you see 3 targets are there. Okay. I will tell this thing. First, let us at t equal to k minus 1, let us decode what it is happening. You have 1, 2, 3, 4, 5. 5 gentlemen are there, or 5 targets are there, 5 objects are there which your sensor is recording. Now, you see how many sensor has given, you should give 5 measurement, but due to clutter it will give more. So, or it could be less if it is a misdetection, it could be less also. There is no guarantee, this is purely stochastic, purely stochastic. So, you see how many 1, 2, 3, 4, 5, 6, 7, 8. So, for this one, this gentleman has given 1, for this one this gentleman has given 1, 2, 1 false alarm also, 1 could be true target also well. Here also 2, here also 2, here at least 1. Okay. Now you have running say 5 Kalman filters, Kalman filter 1, 2, 3, 4, 5 up to t k minus 1. When you got now this much measurement at t equal to k minus 1, how will you know now 8 measurements I am having, which measurement belongs to which target? So, which measurement you will use your Kalman filter estimation update for 5 sequential Kalman filter, which you will use? You do not know. So, you have to solve this problem statistically. Similarly, now go t equal to k. Now, you see 2 targets are off, it is only 3, 1, 2, 3. How many now you are getting? For 1 you are getting 3, 1 you are getting 1, you are getting 2. Again another confusion. So, each and every scan you have to face this confusion. Now, you have to resolve this confusion. How will you resolve it? First, my 2 targets already gone. So, that means these 2 targets could be 2 possibilities. Either these targets are not detected by my sensor, possibility 1, hypothesis 1, or they are dead. Dead targets. Dead targets means these targets no longer exist. Either my platform has moved away with the sensor, or these targets have changed their course and gone different path, take a different route which is beyond my field of view. So, that is not my target of interest. So, whenever it is beyond my field of view for quite a long term, we won't maintain the track of that target. So, they are called dead target. So, this is also another thing. So, what are the now challenges you understand? First is random number of targets and measurements, you already see. So, your target also could be random, your measurements also could be random. So, here you have 5 targets, you have 3 targets. So, 2 targets gone, that means 2 targets either could be out of field of view, and if it is out of field of view for a quite long time, say some 8 cycle or 10 cycle, it is not there in field of view, you have to declare them as a dead. So, you do not maintain their tracks in your track file. Okay? So, they are dead targets. So, and measurement random due to clutter I already told. Next very important thing is the detection uncertainty. There could be a actual target, but due to if the target has some stealthy feature, it could be happen that if the target, because you are taking say an airborne scenario, a typical military airborne scenario, if the target is a stealthy target, so you may not have your reflections coming back. It is possible even for the UIR, say these are all heat seeking kind of a thing. If that heat seeking kind of a thing is kind of masked, you won't be able to see the target. Okay. So, this is called detection or detection uncertainty. So, no matter if scan 1 you got a target present, scan 2 you may get it absent and you get your sensor only pick up the clutter. Okay. So, this is challenging. Next very important thing is called association uncertainty. What is association uncertainty? Association uncertainty means, suppose when you get, suppose this is your actual target which you are maintaining. Now, you have suppose in one gate, I will show you in the next when I will solve the problem, you have multiple measurements are falling. So, which one you will use? Your Kalman filter knows only one as per your measurement update, you have to pick one. So, this is called association uncertainty, or this is called gating, or one measurement could fall into 2 overlap gates. So, this is one target. So, this measurement will be taken by this fellow or this will be taken by this fellow. So, it is a kind of a tussle, it is again a tussle between two kings, who will occupy this land, because this land or this piece of land is between in the border of two different countries. So, who will win it? So, again it is a tussle. Okay. So, this is called association uncertainty. And sudden birth and death of target. Death of target I have explained. What is called birth of a target? Birth of a target means, suppose your target is not there inside the sensor field of view and all of a sudden target has reappeared or appeared all of a sudden, then it is called a birth, it is called a birth of a target. I will show you in the next subsequent slides. So, with this, this is a problem of typical bistatic radar, using that how the actual radar measurements are happening. So, if you see, these are all called radar resolution cells. Okay. So, greens are actual target, actual target or actual kind of a, or you can say that actual measurement. Blue this kind of a rhombus or whatever you say. So, they are actually two targets. So, blue are two targets, green is measurement. So, two targets are very closely spaced to each other. They are within one resolution cell. Radar won't be able to identify whether they are same target. The measurement could be, you won't identify the two, it will give only one measurement. Suppose I am giving a standard example. Suppose two parallel vehicles are there and the spacing of the vehicles are say within centimeter range, say 1 centimeter, 2 centimeter. Okay. And you are tracking with an automotive radar. Okay. Your radar will give only one measurement. It is possible, it is very much possible, because if your sensor cannot resolute, you cannot do anything, obviously you can't do anything, then all these tracking algorithms you cannot do anything, but this is a problem. So, these are called group targets. So, for a certain group of target, if your sensor cannot identify that they are two, you are not giving me two measurements, so it will give you only one measurement. So, this is called a very important thing, this is called sensor resolution problem. Okay. Now, there could be, suppose the sensor, suppose they are identifying, suppose sometime, because though both targets are moving, when they are closely spaced, sensor is giving me 1, whenever there is certain kind of beyond your sensor zone, suppose in this scan, you see this distance and this distance is more. So, now sensor can give me 2, again like this it is maintaining, but there could be a possibility my track, if my algorithms are incorrect, I will give only one target, I won't be failed to resolute. So, my tracking accuracy will need to be improved. Okay. So, this is very important fundamentals in a tracking. So, in this range, in a 2D scenario, in this range and what is that called azimuth cell. So, you have seen, so it could be multiple things. So, this example, you have a false alarm here, there is no target present in this cell. But in this cell you have a false alarm. Here actually there is a misdetection. You have an actual target present, but sensor failed. So, this is a misdetection, failed to give the thing. So, you won't have any update. Here what is there? You have a false alarm, again you have this is a good cell, you have a target and you have a measurement. Here again a false alarm has come. So, this is actually the scenario when you do the radar, and your tracking algorithm should be intelligent enough, it should be autonomous, it should have the autonomy knowledge that it should resolve this kind of conflicting scenarios. Now, I will explain that what is called my target model, little bit more depth. So, target model actually of 3 parts. One is typical simple scenario 1. You have a target, your sensor pick the target, it gives you one measurement. Good, I am happy, simplest steps. You have a target, but there is no measurement is coming. Either target could be sent out of field of view of the sensor, or target could be dead for a long time, it is out of field of view, out of FOV of the sensor. So, that means you have a null set, created. Okay. Now, the very important thing is called spawning target, that is I told, when the target resolution is very minimum, okay, your sensor will pick only one target. Normally in a air-to-air, because I just give an example of car, normally in a air-to-air engagement scenario, what happens? Your enemy aircrafts are coming in a specific squadron, okay, and the squadron leader is front, and all other kind of wingmans, I will say the other aircraft, they are at its back, there could be at its back. So, your radar and your actually your air defense aircraft, which is kind of locking the target, the leader, he does not know that at its back there could be kind of multiple, behind there could be multiple aircraft. So, this is a typical tactics that Air Force people uses also. Okay. So, this is called something called spawning, and all of a sudden you are locking it with your missiles and all of a sudden all aircrafts will come from being from mask. So, they are called spawning. So, they are coming from one parent. So, this is called spawning. So, from one target all of a sudden you got now 3 targets in your field of view. So, one parent, 3 childs are coming or popping up. So, this thing is called spawning. Clutter I have already told, actually there is no target. So, there is a null set, but you are giving me 3. Okay. So, this is called target motion uncertainty. Detection uncertainty, very easy. You have a target, you have a measurement. Ideal scenario. You have a target, you do not have any measurement. That means you miss the target, your sensor has missed the target. In such case, you cannot do anything. No algorithm can do anything. If purpose of the algorithm is to give, if your sensor gives you with the ambiguity, it has to resolve it. That is all algorithm can do. But if sensor itself cannot give you information properly, no algorithm in the world can resolve it. Okay. And this is what clutter I have already explained. Okay. These things you just remove, this is just mathematically I have said. So, from target motion model point of view, you have your physical target, you have your spawning target, and you have your new target or birth targets. Okay. So, it could be a new target also. So, these 3 will consist of your target set. What is your observation set? Obviously, either target oriented measurements or clutter, means detection, anyway you will not get any measurements. Okay. So, with this, this is called target model and measurement model. So, now just to summarize, data association you have to do in a multi-target scenario. What you need to do? You need to first resolve the ambiguity. There could be measurements, there could be clutter, actual target oriented measurement, there could be clutters. You have to now tell that which measurement is your target, which measurement belongs to your clutter. That test you have to do, and second, you have to now do proper estimation of your target oriented measurements. So, in a multi-target tracking, if I ask the definition of a multi-target tracking, it will estimate jointly the target number and the target state. Normally, in a filtering problem, you solve only the target state and state error variance, okay, whatever. But here it is very important to estimate the number of target. So, this is called cardinality. This feature is called cardinality. So, cardinality estimation is very important for a proper multi-target tracking algorithms. Okay. So, that is the main purpose. So, this is the very important feature of multi-target tracking. So, you need to estimate both. First is your target state and then is your target number. Both you need to estimate it properly, because see, in an automotive target scenario, you are moving your BMW vehicle, you are running with a say a long range radar. Okay. With a long range radar you are taking, radar will give you so many reflections, something could be from grass, something could be from tree, something from actual your preceding vehicle, something could be from pedestrian, something could be from guardrail, something could be from road borders itself, or this road, this markers itself, so many things. Now, how you have your job, your data association algorithm has to identify which belongs to what, which is your point of interest, which is not your point of interest. It could be this kind of a thing in an automotive target scenario, a same vehicle you are tracking. So, it is coming from target front, reflections coming from target front, reflection coming from target back, reflection coming from tire, reflection coming from your wheel spikes, everywhere. And now, all this reflection you have to make only one target. So, this is level number 2, complexity number 2, this is called extended object. So, that we won't taught here, because this is too advanced, we won't go into this. But at least data association, you assume it is a point target. Even a point target also, you can get reflections from multiple sources. Now, you have to say which is your point of interest, where you will put the brake, where you do not put the brake, okay, based on your sensor. That is the purpose of an autonomous systems. Okay. So, with this I would like to thank you all for this lecture session. Next subsequent lecture, what we will do, we will take up something called multi-target tracking data association problem, how to resolve it, we will discuss. Okay. Thank you for your time.